All right, welcome back. We are GAME3001. That's Artificial Intelligence for Games. In the winter 2022 semester at George Brown, and it's week 12, part 1 of our broadcast. And this week we're talking about goal-oriented behavior and rule-based systems. So last week what we did was we talked about behavior trees. We talked about 3 different kinds of nodes primarily: selector nodes, sequence nodes, and decorator nodes. And I've kind of put together, I was in the middle of putting together a diagram for you guys last week where we were talking about if we were going to put one in from a behavior tree perspective, how would it look for assignment 4? And this is kind of something that it might look like. So let's take a look. So again, you have a selector node. Selector nodes, remember that we talked about before, could be either child could be successful in order for the entire node to be successful. Okay, so let's think about this. So let's do this one. So this one here is, let's suppose this is a decorator, and a decorator might be something like repeat until fail. It might be something like that. And then it goes into some kind of sequence node, right? And the sequence node would start with its leftmost child, and it's the leftmost child is actually a selector node again, and it could be something like this. Has the player been detected? No, let's suppose, right? Well, now I'm going to try the second child. And the second child might be an action, like patrol. So for example, now I'm in patrol mode. Patrol mode returns success, right? Success goes to the next sequence, right? And then now back into another selector. Is the character or the player within a specific radius? No. Okay, fine. Then we can try the next child, which is move to line of sight. Okay, so then if they're not in the radius, and if it hasn't been detected, we can try to move to somewhere where we have line of sight. Okay, well, let's try and do it. Let's move to line of sight. Okay, go to the next node. Okay, now this one is repeat until fail, just like this one up here. And it might be a sequence that starts like this. Do we have line of sight? Right? Well, we would, as an example, because we're moving to line of sight, right? So let's say we have line of sight, that's true. And then what ends up happening is, we're here, and now we have a choice to decide which one of these works. So are we in close combat distance? Let's say no. Okay, fine, then move to the player, all right? And then we're going to the next sequence, attack. Now that we move to the player, attack. Okay, cool. This is a inverter node, like we talked about again. Okay, that means, is the player dead? No, that's fail. Well, we invert it, that's success. So now we move to the next one. Is the character's health less than 25%? No, that's a failure, but we invert it, that's success. We've done all these things, and we go back up here. It says repeat until fail. So we keep on going until one of these 3 conditions is going to be the way. So in other words, either I've lost line of sight, or I can't attack somehow, or can't move to the player. As an example, the player's dead, or my health is less than 25%. So if this fails, it's going to fail up here, and then it's going to be, this is a repeat until fail, right? So now that it's failed, it's going to go here, and the character is going to flee. It doesn't matter if if the player is dead, or, as an example, the actual player is dead, or my health is less than 25%, either way I'm going to flee because the game is over, right? So it can work like something like this. One thing to note when it comes to behavior trees, and we talked about this when it came to decision trees, way easier to implement. We did an implementation in Lab 7 Part 1. Lab 7 Part 1, we kind of built a tree class with you guys on Thursday of last week. We also added some conditions, and we added some actions. Alex added some Star Trek flavor to it as well to make it interesting. And it was kind of a really neat journey and exploration into how to make a decision tree. Now, this week, we're going to change that. We're going to modify it even more, and maybe take that decision tree and put it inside of the actual autonomous character's brain, as opposed to it being part of the scene class, where it maybe doesn't belong. Okay, so we'll talk about that a little bit in a bit. All right, so that is what we did last week. Questions around the stuff we talked about last week: behavior trees, and even the lab that we did. Any questions at all or concerns? I know this is all new stuff for everybody, and a lot of it sometimes is we can kind of consider academic. Like you look at it and you're like, okay, so how would I implement this thing? You know, a decision tree or a behavior tree or a state machine. How do I do those things? And the how-to part is always the most difficult, thing. Students often ask things like, "Where do I start? I don't know where do I start." And we talked about this before, right? And it's like start thinking about when it comes to implementation details, what structures, what data structures you require in order for you to pull this off, right? One of the tools that Alex and I are working on is some kind of visualization tool to even help you visualize decision trees in the future. All right, so let's continue. So this week then we're shifting gears and we're moving towards a different way of doing things. Again, we're adding more complexity to the behavior and more challenges for the AI to be as believable as possible. Again, the goal of AI designers is to make their AI agents or autonomous characters, you can interchange those two things, as believable or as human as possible. The more human they are, the more challenging they are for the player, that's us, when we're actually playing with them, right? Simple AI is always easy to defeat. We can predict what they're going to do. And as our capabilities as a player improves, for example, I get more items in a game, or I just get better at my reaction time because I'm practicing in a specific game over and over again, AI becomes easier and easier to beat. Jack says, would a dialogue tree fit into what we are talking about? Absolutely. Yeah, because I think the dialogue is based on action reaction, right? So you come up with a set of actions that you're proposing for your character to say. Let's say, for example, I have a dialogue. I'm selecting a dialogue myself, let's say, and then the AI has a dialogue tree that they're going to respond to your trigger. You're basically selecting something, and then from whatever you selected, they're going to respond, right? So that is kind of the same thing. Stimulus, whatever that stimulus is going to be, and some kind of response, right? Stimulus could be input from the game world. Remember, we talked about external knowledge and internal knowledge. And today we're going to be talking more about internal knowledge. Things like, what are the goals? What are the beliefs of your AI? So a little bit more esoteric, but actually can make a very believable system. Let's talk about this a bit. But first, before we get there, again, I'm just looking at admin here. Lab 7 Part 2 is going to be today, or this week, I mean. Things that are still due. Assignment 3, the due date has been moved for people who don't know that. If you missed Assignment 3 somehow, or you think you did, you haven't. The due date has been moved to this Sunday, April the 3rd at midnight. We did this to accommodate workload, the stuff that we were talking about last week. Assignment 4, still due week 14, right? So that is kind of the last week of, or second last week of class, Sunday, April 17th at midnight. And assignment 5 will be a presentation component to replace your final exam in this course, which is going to be really showing off your assignment 4 and how it works. So you're going to be doing that. And we're going to have pretty much the last week of class demoing your little assignment, talking about the things that you did to pull it off. So again, that's why assignment 3 and 4 kind of build together. It's an important thing for you guys to put it together, as it can be very interesting for everyone to take a look at it as well at the end. Okay, so that's what's coming up. We're sitting again, just from a timing perspective, here at week 12. So we really only have 4 weeks left, including this week. So this week, and another 3 weeks after that, and then it's done. We're done for the semester. I think there's a lot that we've covered this semester for you. So let's recall things that we've already talked about. In the first half, we talked about things like movement and steering behaviors, how to move an agent around. You should be very comfortable at this point understanding how to do steering behaviors, basic steering behaviors, seeking, fleeing, arriving, looking where you're going. Those are basic steering behaviors that you should know how to do right now. So we asked those from you, when you're doing assignment 3 and assignment 4. It's expected that you know how to do that, right? How to move things around. We also did pathfinding, and there's nothing wrong with adding pathfinding on top of, some kind of decision making. So pathfinding and decision making makes it really cool because we've given you a bunch of nodes, path nodes that are inside of your labs, and if I wanted to find the shortest path, it might be a lot easier now because the obstacles are quite large. So the shortest path to a particular to the target, and we don't care about, in this case, if I'm thinking about neighbor nodes, right? If I'm going to think about that and mapping the entire game world right now, we have the same number of game nodes or path nodes that we had in tile nodes when we first did A star, as an example. But now you could, if you really wanted to, you could map all 8 neighbors, with the same mapping algorithm. And I think the great thing about that is you can get the shortest path. You won't get stuck as easily, and you'll have an AI that moves in a kind of a good pattern. Or you can stay away from that for assignment 3 because it might be complex to code, and just think about going to the nearest node, or I'm talking about assignment 4 now, seeking the nearest node that has line of sight. Okay, that's kind of the way it can be done as well. Okay, nearest node meaning the distance between the autonomous character, the ship, as an example, in our case, and the target. Okay. All right, so that is where we're sitting at week 12. Next week, we're talking more about utility theory. We're touching on it this week as an example. What is utility? And then followed by strategic AI at week 14 and tactical pathfinding, which is kind of neat as well. And then getting into machine learning basics in week 15. That is our topic. However, I just wanted to put it out there that depending on how this goes in week 15, we may elect for the labs because there is no lab happening for the last week. So the lab itself will be used for you to do your presentation. Okay, so that's what's happening there. And since the labs are 2 hours and we have kind of groups of students, then you'll be allotted enough time to present your lab, present your assignments in the last week of class. Just letting you know. So that's the plan. And I'm updating you with this again because some of us have forgotten. As an example, we haven't thought about how to do stuff or whatever, or what to do next, or what's coming. So that I'm kind of putting it out there for you. Questions around the admin part, any kind of the status of the course, where we're at with it, as well as what's up and coming. Okay, if there are questions, please let me know. Let's talk about goal-oriented behavior and what that whole thing is. So it's a little different. We're shifting gears in this lecture compared to what we did. We were very algorithm heavy so far that we've been talking about. We used a data structure, a tree data structure, or a state machine in the last few lectures. This time around, we're doing things slightly differently, where we're making our own custom structures to fit what we're doing here. So let's talk about this. So again, we've so far focused on approaches that react to some kind of set of inputs, right, provided to the autonomous character. So it could be line of sight, could be some kind of sensing radius. It could be that they have knowledge of the game world externally, that they've passed through. So for example, knowing that a character is near, the character has been detected or not, maybe the alarm has been raised, a bunch of different states that could be triggered that the character knows about. And these are considered inputs. So, or some kind of criteria that is going to cause the character, the autonomous character or the agent, to do something. Okay, and we have some kind of behavior, and that behavior is going to select an appropriate action, that we're going to that the autonomous character is going to take based on its stimulus. Whatever we stimulate it, it's going to be stimulated from the game world. It's going to react. Okay, and but there are no implementations of any kind of desires or goals. I mean, sometimes you can think about it and it's like the character is going to behave, but there isn't an underlying motive for the character. We might use a behavior tree combined with some, goal-oriented behaviors. So I'm going to go through a decision matrix, let's say as an example, a decision tree. I'm going to follow a decision tree, but it's going to be triggered by maybe a motivation, something like that. I might use a behavior tree with this, to follow a sequence of behaviors based on the fact that I have a goal that I have to achieve. Okay, that's a different thing that we're doing. We're talking about now. So far, again, we just have the character reacting to input or stimulus. Okay, and it's possible, of course, to make the autonomous character seem like it has desires and goals. Let's talk about this. So again, when I say seem, a lot of times what we want to do is we want to create a simulation of what the autonomous character is going to do if it were in a situation where its goals or motives were challenged. Okay, let's talk about them. So here's an example. An autonomous character whose desire it is to kill an enemy will, one down, as an example, react to the appearance of an enemy by attacking and search for an enemy where there is a lack of one, patrol, okay, or do a search. The same character may also have the apparent desire to stay alive, in which case it will take account its protection, so maybe some kind of defenses that it's going to build up, some kind of maybe react to low health, or respond to the presence of danger, raising the alarm, those kind of things. So again, the underlying structure may be reacting to input, but the autonomous characters doesn't need to appear that way. We can make it different. And that's what this section is all about. So let's think about people simulation games like The Sims. Okay, so this is a different kind of AI, right? Because we want to make the characters, kind of demonstrate their emotional and physical states. So example, maybe the Sim is going to eat when they're hungry or sleep when they're tired, chat with friends when they're lonely, do all kinds of stuff, right? We could simply run a decision tree. That's a way of doing it. That selects available actions based on, let's say, emotional and physical parameters. Am I sad? Well, then I call up a friend, as an example. Am I hungry? Then I eat, those kind of things. So that's pretty okay. But the problem with that is The Sims, it can be quite complex, and the resulting decision tree might be large, very, very huge, right? So that may not be the right structure as an example for doing this kind of thing. Maybe a better approach might be to present the autonomous character with a suite of possible actions and have it choose the one that best meets its immediate needs. So I have a bunch of actions, different way of thinking, and I'm going to choose one that meets my goals. And this is what goal-oriented behavior is. Goal-oriented behavior is also called GOB. I'm not going to use GOB in my example, maybe only once. And it's really explicitly seeking to fulfill the character's internal goals, whatever they are, right? And goal-oriented behavior may mean a lot of different things to different people. Sometimes it's referred to goal-seeking, decision-making algorithms. So kind of things that are combined together. So again, look at this decision-making part. We can have our algorithm use something like a decision tree in part of it, or a behavior tree, or even a state machine. The implementation details for the response to a stimulus, all right, as an example, or things that it's sensing, or so in order for it to fulfill a goal, that is totally different. So remember in A4, on assignment 4 for us, we've given you two types of loadouts: a close combat enemy and a ranged combat enemy, right? So two types of enemies. But what are their goals? Are their goals only to attack and kill the player? Maybe, but what if they have other secondary goals like gather resources, build a fort, do whatever they're going to do, and those kind of behaviors, if we wanted to extend the autonomous character that we're asking you to make, can make it so it's much more complex, but also very neat in a game. Really kind of colors the game, the way it works, and adds a different flavor to the mechanics in the game world. So let's talk about some of those kind of possibilities. So again, goal-oriented behavior, this blanket term that covers any technique that takes account goals and desires. And so, we can think about some goals and desires. We can also kind of convert the word goal or desire to something like motive. And for us, I'm going to say this in the next slide, for the most part, we're going to kind of talk about goals, desires, and motives as one thing, but they may not be. Here's an example of Sims motives that you might have to achieve as an example. And they might have certain motives that you need to accomplish when it comes to 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 make the sim happy, right? So here's goals. Let's talk about goals for a second. So again, um, the thing when it comes to goals or motives is that there's some kind of currently active goal that is kind of going, that the autonomous character might have. Each goal, then, if we're going to translate it into computer science, you know, techniques, let's say, might have some kind of value, a number that represents its insistence, how important this thing is. Okay. And a goal with a high insistence, a high number, right, will tend to influence the autonomous character's behavior more strongly, as opposed to something that has a low insistence. Let's take a look at some examples in a few minutes. So really what we want to do with the autonomous character is try to fulfill its goal. That's what we want it to do. And to reduce its, the goal's insistence, whatever that goal is. And again, you can have multiple goals that you want to fulfill. So here's an example in Subnautica where you have a bunch of goals, right? You have a health goal because you have to heal yourself, right? Keep your health high. You might have a food goal, and this is in survival mode, let's say, where you have to collect enough food. And over time, we're going to talk about how time can vary this goal. It's going to drop, and you're going to have to continuously feed that goal, which is like literally gathering food and eating it, right? And then the other one is water. You need to drink water. All right. So those are kind of goals that you have as a player, right? But it could be the same kind of goals that you might give an autonomous character, that they need to keep their health, themselves healthy, make sure they eat, right, and have some water, and also have enough oxygen if they're kind of always diving in the water, in order for them to survive, because they need to have some kind of level of O2 in Subnautica. So again, one thing to note is the autonomous character will try to fulfill its goal, reduce its insistence, whatever that is. And some games allow goals to be completely satisfied, again, such as killing an enemy. Other games have a fixed set of goals that are always there, and they simply reduce the insistence when the goal is fulfilled, so it goes down. And then in our case, a zero value of insistence is equivalent to a completely satisfied goal. We have a zero value. All right, let's talk about that in a little bit more detail. So for the purpose of making great autonomous characters, we talked about this already. Goals, motives are the same. We're not going to talk about too much about this. And now that we know what goals are something that needs to be fulfilled. A goal has some kind of an insistence number, a value that we have to meet, right? But then we have to take actions. We know what actions are. We have a suite of possible actions in order for us to meet that goal, whatever it's going to be. And again, sometimes these actions can be generated, and sometimes it's common for items in the world, as an example, to kind of trigger the autonomous character to take that action. A good example of that might be boil kettle as an action. An empty oven might do things like insert raw food. That might be an action that is available, for autonomous character to take when they're hungry, right? Or if an enemy, if we're the player character, we're the enemy, it might introduce the attack me action. It's a different way of thinking. So, hey, there's an enemy near. Well, guess what? The attack me action now is part of my list of actions that I could possibly take, because the enemy happened to just come into the room, right? The enemy wasn't part of the room before. Now they are. And now the attack me action, or the attack action, is going to be something that we want to take. Same thing with the door. The door, if it's unlocked and we're leaving, as an example, an area to patrol, there might be a lock action when you leave the room. Let's say you're in a guard tower and you're leaving, you might have to lock the door because you want to keep it safe. One of your goals, I'm thinking about an autonomous character here again, an agent, an AI, might be to keep the guard tower secure. That might be a goal. So every time they leave to do a patrol, they lock the door. That might be something that they do, right? But what if they're in the middle of locking the door, and you're watching them as a player, and you know that they do this, right? They lock the door before they leave. In the middle of locking the door, they haven't completed the action, you shoot them and you start fighting with them. And that might be something that, again, creates more complex behavior and even more different kinds of gameplay, gives the player a lot more agency when it comes to a more believable type of game. And again, any of this stuff, why are we doing AI to this level, or even talking about goal-oriented behavior? We're talking about it because we want to, create a level of immersion for the players, right? That is higher than just making the lower level AI, where the suspension of disbelief is going to go away. If now you're playing almost like a little, kind of a game where you may not be immersed in the game world if the AI is really dumb, like if it's repetitive, right? And there's no need for if there's no reason for the AI to be repetitive, right? And we all play games like that where the AI kind of does very, very simple actions, reactions, all right, and they're fun to play. But where the games are really fun, where we really get immersed, is where the AI is way more complex. They do more complex actions, and you're going to try and anticipate what they're going to try and do, and they're random enough or they're human-like enough, that the game it becomes very challenging and interesting. So on that, let's continue with actions. The actions available depend on the current state of the game, right? So not all actions are available all the time. So whereas in a decision tree, all actions, kind of, and the leaf nodes of the tree are available, right? It depends on, which state the character's in. Let's say, for example, if there's some kind of condition that is met in a decision tree, it's going to quickly go from one kind of condition to the next, and finally it's going to end up at some kind of predetermined action. Not so in goal-oriented behavior. In goal-oriented behavior, you're going to not even have that action as a possibility, as an example, not even part of the list or of the suite of actions, depending on a particular game state. Okay, so there must be something that's going to add that action to almost like a queue or a list of actions that are available, right? So here's an example. The empty oven might check if the character is carrying raw food before kind of submitting its insert action. So the insert action doesn't even exist until the character's carrying raw food, because the raw food is a dependency for the oven, right? So there's no raw food, then the dependency for the oven to insert food isn't even met. So therefore, that action wouldn't even be available. Okay. Let's take it further. An oven containing raw food does not allow more food to be added because, well, it's full. There's food already in it cooking, so you can't put more food into it, right? So again, this is like, it's not only a dependency, but a constraint. You can only have this much raw food in an oven. If that action, insert raw food, isn't even available because it's full, right? Again, these are very simple things that are very easy to understand for us humans. But try and code that from an AI. The AI might try to add food into something that's already full, right? Unless you've constrained it. Say it's only available when. Similarly, the door exposes an unlock action if it's already locked, right? Or maybe an insert key action first before unlocking is even allowed. So do you have a key? No? Okay. If you don't have a key, then maybe insert key is not even there, right? And sometimes giving the insert key action to the player might be, kind of giving them a hint of what to do, right? That's also not a bad thing, depending on the type of game you're playing. More about actions. Okay, so actions, they're added to the list of options, but they're also rated against each motive that the autonomous character has. So, and this rating that we're talking about, is how much impact the action would have on a particular motive. So, okay, so I have an action, but when I take that action, what does it do against my goal? So if I have a goal, motive, desire, whatever you want to call it for an autonomous character, taking that action, how is it going to satisfy my goal? And how is it going to reduce my insistence, that goal's insistence? It's going to reduce the numbers, right? So I don't want to have, I want to do an action that makes sense. In other words, we'll talk about this. Each action maps to a list of goals that can be achieved. You might have multiple goals that each, or multiple actions that can be that can achieve the same goal. Example would be shoot action could fulfill a kill enemy goal if that's what your goal is, right? As can a spring trap or some other kind of action. It can still kill the enemy, but you can do it in different ways. I can shoot it or set up a trap. Okay. So again, the goal that an action promises to fulfill might be several steps away as well. That's also a thing for actions. So example, a piece of raw food might offer to fulfill hunger. That's the fulfillment promise, right? And if the autonomous character picks it up, it will not become less hungry, right? Until it actually gets the food cooked, and then they can eat it. So it might take several steps or a sequence of actions in order for it to complete or fulfill its goal to some degree, okay? And so we have a set of possible actions so far and a set of goals. This is where we're at. So actions and goals. And we want to map actions to goals. And we want to take the best action that, we're going to take based on, what goals we have. So here's a couple of goals. We have, again, we're going with the people simulation. We have an eat goal with an insistence of 4 and a sleep goal with an insistence of 3. Okay, so here's some actions that map to those goals where I have an action that's get raw food, right? If I get raw food, it says I'm going to reduce my eat goal by 3. Okay, interesting. And get snack, my eat goal is going to reduce by 2. Okay, that's interesting. Sleep in bed, my sleep goal is going to be reduced by 4. And my sleep on sofa, my sleep insistence is going to be reduced by 2. So there's different kinds of actions that can do different things according to the goals. And if I have an insistence of eat 4 and sleep 3, and let's suppose there's a 5-point scale. We're on a 5-point scale of 0 to 5, where 5 is very insistent. So this person that we're looking at is hungry, fairly hungry, and also sleepy. So quite sleepy, quite tired, right? Not tired, but kind of in the middle. They're getting tired. How about that? All right. So that is something that we can look at when it comes to this. So again, it having those goals provides actions, right? So again, the action of get raw food, right? Or as an example, that has nothing to do with any kind of stimulus from us as the character, as the player. It has nothing to do with it. These things are going to run autonomously. They're going to do their action whether we're there or not. They're going to fulfill their goals, and we're going to see them doing stuff, and we're approaching, like they're, characters in a book. That's the idea that we want to pull off, and it's very challenging. Okay, so we're thinking about simple action selection now. So we're just selecting an action to give some kind of intelligent looking behavior. That's what we want, right? And a simple approach would be just to choose the most pressing goal, the one with the largest insistence, and find an action that either fulfills it completely or provides it with the largest decrease in insistence. So in this example above, right, because our, eat 4, right, our insistence is 4 out of 5 points, let's say, and we can reduce it the most. We can reduce because this is the highest insistence, we're not even looking at sleep, because we're only looking at the highest insistence, a goal. We might have a set of goals, and we're looking at the one that has the highest number, 4. And then now, okay, so what can satisfy it from these actions? Well, I can do sleep in bed, sleep in sofa, but that doesn't match with my highest insistence, right? And as an example, so we wouldn't take these 2 actions. We would only consider get raw food or get snack, and since get snack only reduces it by 2, and get raw food decreases it by 3, we choose the get raw food action to match with the higher insistence goal of eat. Does it make sense? So this is good. And the change in goal insistence that is promised by an action is a heuristic estimate. Okay, so it's, again, remember when we think about an estimated function, like something like we did Manhattan distance in the past. We also did Euclidean distance. Those were evaluation functions. Those we kind of predicted, what how we're closer when we're doing pathfinding, and we called it a heuristic. It's an evaluation, an estimate about how far the distance is from the player to like the goal, like as an example, right? Well, here it's kind of the same thing. We're making it. We're kind of estimating, the action based on its utility. We're going to talk more about utility theory next week. All right. So, what is utility? And again, what we want to do is that it might be how much use it's going to be for this autonomous character, and the character naturally wants to choose an action with the highest utility, the highest reduction in insistence, if you will. Okay, so if more than one action can fulfill a goal, we could choose between them at random or simply select the first one we find. Okay, the first one that seems applicable. It's really up to how we want to program the AI. Unfortunately, dealing with the most pressing goal may have some side effects, right? So again, not people in the real world have multiple goals, and sometimes your goals conflict, and so too might something like that happen for a game AI. Let's suppose we're going to go back to the people example, and we're using a 5-point scale again, and we're going to give two insistence, kind of two goals with fairly decent insistence. One of them is an eat goal, so hunger, which has an insistence of 4, and a bathroom hygiene. Let's say you have to do something with the bathroom. You have to go to the bathroom, which is an insistence of 3. So kind of a medium to medium high goal from a 0 to 5, let's say. And there's a couple of actions available to you. You can drink a soda, which would reduce your, your eat insistence by 2. So it's going to drop it from 4 to 2, but it's going to increase your bathroom insistence from 3 to 6. And it can't go to 6, so it'll go right to 5, right? So it'll be like, you need to go to the bathroom now. It has to be done immediately, right? Because you just drank a soda. The other one would be, I want to visit the bathroom, right? And visiting the bathroom would reduce my bathroom insistence to 0, right? Which is good. That's what we want. But if we use the most pressing need, like we talked about earlier, that's something we said, then eat would be the main pressing need, which means the action to visit the bathroom wouldn't be even here, and we would be in trouble. And especially if, let's say, if the bathroom, if you went higher than 5, you could hurt yourself. Let's say somehow it can actually cause damage or whatever, or I don't know, it can reduce your speed or do something to the character that's negative, some kind of side effect. So again, that is something we want to avoid. And how do we take into account multiple goals where we want to service the one with the highest insistence, but yet we have other goals too. And, taking an action is going to influence the, not just one goal, but 2. It might serve both, but also negatively influence the other one. Okay. So what do we do? Well, we can think about this in terms of looking at this, all the goals as a whole, and we can kind of think about the overall discontentment of a character. So we have insistence, and then we can say how discontent, how unhappy is the autonomous character based on the insistences of each of its goals. We can add those things up. That's one way of doing it, right? So we can kind of add them up, and then what we want to do is we want to reduce the overall discontentment level of an autonomous character by doing one action. So the action is not going to be just on setting up a goal, but now it's going to be look at the discontentment as a whole for the autonomous character. So what this could look like is, I'm thinking now that, and how do you calculate, first of all, discontentment? How we can do that? There's a couple of ways to do that. We could certainly add the numbers up, but sometimes, you might have insistence values that are higher than others. You might have, for example, instead of adding them, making them even, you might have different weightings you might want to use as well. A lot of times what really works well is squaring the goal value. Okay, squaring the goal value. So let's suppose that I have an eat insistence of 4 and a bathroom insistence of 3. Then if we square both those values, then eat would be 16 and bathroom would be 9. So 9 and 16 is 25 discontentment starting off. That is your overall discontentment for your character at this point, this state in the game. So then there's two different actions, and you're going to have, kind of what the effects would be, and then what your state would be after you took that action. So you'd have an after effect, if you will, right? So let's think about this, right? Overall, my discontentment is 25 starting. If I take the drink soda action, then eat would go down to 2 by 2, and bathroom would go up by 2 to 5, right? And if we did that, then taking this action, right, after we eat with 2, bathroom is 5, 2 times 2 is 4, and 5 times 5 is 25, 25 and 4, your discontentment actually is going to go up. It's worse than where you are right now. You're bad now, you're at 25 discontentment, but it's going to go to 29 if you take this action. So then the action for drinking soda would not be a choice, because you want to go with the action that has the least discontentment for the character. Okay? So if you think of it that way, then if we said just bathroom minus 4, right, where then your bathroom cannot go lower than 0, go to 0, right? But then your eat would go to 4, because let's suppose that it would stay at 4 where it is right now. So eat would be 4 times 4 is 16, and so your discontentment would drop to 16, which is, again, if you think about this, is the lowest discontentment between these two actions. And if we were to loop this over here to the top again, and you see that if my discontentment happened to be 16, right, as an example, and then if I was going to eat, right, and my bathroom would go to 2, I would drop this to 2, and I would increase my bathroom to 2, so it would be 2 times 2 is 4, and then 2 times 2 is 4, and 4 and 4 is 8. So actually my discontentment would drop down to 8 from 16 if I was to drink a soda after I went to the bathroom. Does that make sense? So that's why adding it up isn't the same as, kind of squaring. Squaring makes more sense. So now in the new state, if I was going to just loop through this scenario over and over again, right, my eat would be 2 and my bathroom would be 2, right? So now what would I do? 2 and 2, again, I would be a discontentment of 8, and I could take a drink action, which would drive my eating down to 0, and it would drive my my bathroom up to 4. 4 times 4 is 16. I wouldn't take the drink soda action, that's for sure, right? What about going to the bathroom again? Well, if I had an eat of 2 and a bathroom of 2, then taking a bathroom of 4 would drop it to 0. So that would be the best action again, because I would go down to a 2 eat and a 0 bathroom. And a 2 eat would be that, and again, this is just bathroom and eating, right? A 2 eat would be 2 times 2 is 4. So my discontentment would go down to 4. So I'd probably hit the bathroom a couple of times in this scenario, because those are the actions that are available to me. Questions around insistence and discontentment, okay, and goals. Any questions around this, the understanding piece? Because this is the kind of stuff that we can make a more complex AI. What are your thoughts, guys? And again, I think one of the great things about this is it creates almost like a context for why the autonomous character or your enemies in the game, or non-player characters, which also are autonomous characters, why they are doing the things that they're doing. Why are they attacking you? Why are they going to defend their home, right? Why do they care about those kind of things? What is their motivations? What are their goals? If you attack another character in the player's home, as an example, you're not attacking them, so they're not going to be threatened themselves. But maybe one of their goals is keeping the family safe. And there's a lot of discontentment. The discontentment goes from 0 to 5. They have to act right away if you're attacking a family member, something like that. Or maybe a team member, if it's not necessarily a family in their home. You're in some kind of headquarters, and you attack a team member that's in some kind of, some kind of faction that you're in. They're all going to attack you. They're going to turn around and do something to you, because now they're going to defend their team member. All right, so that is, kind of your actions and how it has effects, or your autonomous character's actions and how it has effects on multiple goals or desires, motives. So again, to make a decision, each possible action is considered in turn, and a prediction is made of the total discontentment after. So that's what we just showed, and the action that leads to the lowest discontentment is chosen. Okay, this is a summary of what we just talked about. So that's kind of one simple selection criteria, one more complex one. But often it's not even that simple. Sometimes, and quite often as well, there's timing involved, okay? Or like we said, a dependency chain, a chain of actions that must be taken because, well, you can't do that particular action yet, right? You have to satisfy the dependency that you need, some kind of dependency in order for you to take that action. And the dependency can have a couple of different layers that we're going to talk about. Let's talk about this right now. So, so again, let's think about this informed decision idea right behind this. In order to make an informed decision as to which action to take, the autonomous character needs to know how long the action will take to carry it out. So again, example, it might be better for an energy deficient character, someone who doesn't have a lot of food, right, as an example, to get a smaller boost quickly by eating a chocolate bar, as an example, rather than spending 8 hours sleeping, right, because they're energy deficient, right? Actions expose the time they take to complete. So that makes more sense now. Now it's even another layer of complexity that we're adding in. And what that does is it enables us to work that into the decision-making process, okay? So actions that are the first, of several steps to a goal will estimate the total time to reach that goal, right? So for example, I might have pick up raw food action might report a 30-minute duration to pick up the raw food, right? And the picking up action itself is almost instantaneous, but it might take several more steps, including long cooking time before the food is ready, right? So picking up raw food, the whole thing the reason why it's estimating 30 minutes in game time is because there's a lot of other steps involved, almost like a chain of steps that needs to be taken, a dependency chain. So again, what you want to think about is that there are two components when it comes to timing. One of them is some kind of time to complete, and the other one is maybe you need to get to the right location in order for you to meet the criteria in order for you to start that action, whatever that is. Okay, so maybe I can't cook, the food right now where I am. I can't cook it just like in random. I need to have some kind of cooking station that's available to me, right? And that's available in many games. Valheim is a good example of where you need a cooking station. One of the latest popular games that's out there right now, Core Keeper, as an example, again, an indie game that's made, I think, with Unity as well. By the way, all the games that we've talked about so far, other than The Sims, made with Unity. Subnautica made with Unity, Valheim, Core Keeper. A lot of games that we're talking about are made with Unity, and we're going to be talking more and more about Unity as your time continues here at George Brown. So let's think about this for a second. So you have some kind of time to complete, and you need some kind of cooking station or some kind of device, some kind of dependency in order for you to do it. It could be a location. It could be a location in something else. Like, for example, maybe you can't cook, in the rain, because that is you can't cook in the rain in Valheim, as an example, because the fire that you're making, which is something they have to do, almost like it has to be dry, right? So you have to cook in a dry location. So you have to have your fire running. It can't go out, and you're not going to be able to cook unless you have a cooking station, and it has to be in a dry location. Otherwise, you won't be able to kick off the cooking action. Okay. Now again, in these games, the NPCs we're talking about, there are no NPCs like this. I'm just talking about player actions, but I'm using the example of a cooking station as something that might be a dependency for an autonomous character, an agent. Okay. All right, cool. So right. So because game time is often extremely compressed, right? A lot of times we're not going to do a one-to-one. It's not like 30 minutes in game time is 30 minutes in the real world. That's not really the case. I'm thinking Minecraft, where your time of day system is kind of, you're moving from kind of a day cycle to a night cycle. This kind of thing that's happening, and it's progressing quite quickly. Minutes translate to hours in game time, that kind of thing. So so it's compressed, but it's going to take some minutes in the real world for you to complete an action. So example, if it takes you to cook a piece of raw food, let's say a minute of real time, right? Could be a long time in terms of what's happening, especially when you have to do other things. Let's say you have a bunch of needs for you to meet as a player. Well, it'd be the same thing for an autonomous character, right? And the longer that the action takes, especially if the character needs food or they're tired or whatever, so they're an energy deficient autonomous character, it might end up being that they die, because of that. Because especially if your food level goes down to 0, you start taking damage a lot of times in some of these games, and you start the damage itself is enough to kill you, then the character might die based on how long it takes for them to cook the food. Okay, so that's something that we can talk about. So when we start using time in our decision making, we really need to think about a couple of things, right? One of them is we should incorporate time into our discontentment, okay? And we could prefer actions that are short over those that are long. So shorter actions, they may not reduce the discontentment where we want it to be, but at least it'll be like kind of choosing picking the lowest hanging fruit kind of thing from a tree. Instead of climbing the tree and getting up there, this analogy, then we pick the lowest hanging fruit because it's the one that's quickly available, something that we can get at right away. So again, it's easy to add to our previous structure that we had before. And however, a more interesting approach to do this, might take into account the consequences of the extra time. Like what happens if you wait? Maybe your discontentment changes over time if you do nothing, right? So in some games, goal values change over time. So example, a character might get increasingly hungry, tend to run out of ammo, gain more power for a combo attack the longer it's waiting. Like there's little things that can happen that can increase or decrease discontentment. So when goal insistencies change on their own, not only does an action directly affect some goals, but also the time it takes to complete an action may cause others to change naturally as well, which is something that we want. And this can be factored into the discontentment calculation we looked at previously, right? If we know goal value will change over time, then we can factor those changes into discontentment calculation. Let's talk about how that might work. So here is an example, a couple of goals again. We're using the people example again. We have eat, and eat changes at +4 every game hour. Okay, that's what happens. So I'm going to get hungrier and hungrier every game hour, right? So that means maybe slices of game hour. That means every 15 minutes, right? As an example, I'm going to, this is going to tick up 1 notch every 15 minutes, right? So, and maybe the 1 notch is one point. If it changes at +4 per hour, that's 1 point every 15 minutes, right? 15 minutes of game time. So, or bathroom, it changes at 2 points per hour. That means 1 point every 30 minutes, okay, which is not as bad, right? So that's how it looks like. So those are the insistencies, plus you have the rate of change per hour, which is what you're looking at. So here's some actions. If you eat a snack, as an example, eating a snack reduces your eat insistency by 2, right? And it takes 15 minutes for this to happen. Well, if it reduces your eat intensity by 2, right, and takes 15 minutes, it actually goes back up by 1. Does that make sense? Because every 15 minutes, your eat intensity is going to go up. Now, I guess what's happening here is when you're eating, you're not actually increasing. You're stopping this rate of change calculation from occurring while you're doing the eating. That's something we also have to think about, right? So while you're eating, you're not going to get hungrier necessarily, right? But every 15 minutes it's going to go up. So in 15 minutes, you reduce your eat to 2. But because 15 minutes, bathroom is ticking along too. Your bathroom insistency is ticking along, and your burn rate is at 2 per hour, right? That means that in 30 minutes it's going to go up by 1, but in 15 minutes it's going to go up by 0.5. So now you can see that bathroom goes from 3 to 3.5. And if you take these and calculate the discontentment by squaring these numbers, this is 2 times 2 is 4, and 3.5 by 3.5. You do that, and then you come up with a discontentment that works out to be 16.25. Right. So again, what did you start from? 4 and 3. right? So your discontentment originally was 4 times 4 is 16 and 9 is 25. You're going to go down from 25 to 16.25, which means that your eat snack action happens to be the best one based on the time it takes to eat the snack and what effects it's going to have on your goals. Phew, right? Eat main meal may satisfy your eat requirement more, but the problem with that is it's going to drive your eat down to 0, but your bathroom is going to go up to 5. 5 times 5 is 25. So actually it's going to go from 25 to 25, which means no change. And you're going to have a crazy desire to satisfy your bathroom next, right? Visit the bathroom, right? So that doesn't make sense. That's not the best possible action you could take, all right? Because your bathroom is going to be really, really high, right? And same thing goes the other way around. If I eat a long meal or visit the bathroom, right? To visit the bathroom, my meal requirements go really, really high because it goes up to, let's say, 5, the highest level, right? Where my bathroom goes down to 0. Again, that's a discontentment of 25, which means going from 25 to one of these two. No real change, no advantage to doing this one. In fact, you get some really bad scores happening with your eat and bathroom, which could mean that eating does damage, bathroom could do damage as well in a game. Whereas choosing an eat snack goal, which may not be as satisfying to one of your goals as one of these two, might be the best choice. Okay. Does it make sense? So timing is also a factor. Timing is also a factor. And what this does, again, is now we have 3 things we've talked about. We've had the insistency of a particular, or the insistence of a particular goal. We have the overall discontentment of the character, right? And we have timing, where your insistence goes up over time, right? So that your discontentment also changes over time, which means it kind of makes your autonomous character continue doing things like hunting for food, or going to the bathroom, or building shelter, or whatever it's going to do, right? And it kind of creates a context for you to play within, in a more believable world, as opposed to, well, you're going to destroy a village because that is one of your goals. You want to do that because you want to, let's say, increase the amount of land that your character has achieve. You kind of add more land to your roster, as an example. Maybe you want to build a bigger base, but in order for you to do that, you have to go and attack a village. When you get to the village, you see stuff happening, and it creates this context for the story, which is really almost like a procedural storytelling technique for the game, which gives you this sense of immersion. Do you really do that? Do you attack the village? What other things can the village do for you? Maybe the village might trade with you. That might be a thing that they might do with a character that they find friendly. As an example, maybe their status or the way they think about you is, right now you're neutral. You're in a neutral state. So they might send a guard to you, as an example, that might meet you and say, what do you want here? That might be part of your dialogue tree that Jack was talking about earlier, right? What do you want here? I'm looking for food. Okay, we have some food to trade. That might be their thing. What are the other things you have to do? Well, enough talk. I want to attack you. So you attack, and then it alerts the village so that you drop out of dialogue mode into fighting mode. There could be a lot of things that you can do, and it can create very complex scenarios, which can make it immersion a lot better. And again, giving agency, more believability to the character, creating this open world idea, as opposed to autonomous characters or agents that do very limited actions. They only attack you, or they do something, right, that are very simple. So one of the things we have to talk about is this need for planning, right? So no matter what selection mechanism we use within reason, we have assumed that actions are only available for selection when the character can execute them. And that depends on, it's kind of like scenario specific, right? So some actions aren't going to be available depending on the context of the game, okay? And we've looked at a method that considers the effects that one action can have on many goals. So again, eating has an effect both on the eating insistence and the bathroom insistence, as a good example. And the final result is often suitable for use in a game without any more sophistication. You can actually get really good just with the stuff we've talked about already. But there's other types of interactions that our approach doesn't solve so far. And again, let's talk about this. Because actions are situation dependent, it is normal for one action to enable or disable several other actions, right? Depending on how you're in, right? What situation you're in. So again, problems like this have usually been designed out of games, and the reason for it is because it becomes a very complex scenario, right? So how do we deal with something like this if it's something that we want to create? If we want to create a more realistic scenario where one action can disable a set of other actions. Here's a scenario. Let's imagine a fantasy role-playing game where a magic-using character, some kind of wizard, has 5 fresh energy crystals in their wand. And let's suppose these 5 fresh energy crystals translate into charges. As an example, I have 5 charges in my wand. Powerful spells take multiple crystals of energy, multiple charges, okay? And the character is in desperate need of healing and would also like to fend off the large ogre that's descending on her. Okay, cool. Let's see what happens. And here are the motives and possible actions that are shown below. So our motive is to heal. Our goal is to heal. Our insistence is 4, as an example. And our kill ogre insistence is 3. So we're in trouble. We're low on health. And our defense capabilities for the ogre is 3. Well, if I look at my total discontentment at this point in time, not taking into account the time it takes to trigger any of these things, all right, just this particular scenario, then I have a 16 plus 9 is 25 discontentment right now, okay? So that's what it does. So I could do a number of different actions with my wand. So one of them was, but I only have 5 charges, okay? So this is a dependency, if you will, right? So if I use if I try and kill the ogre with a fireball, as an example, it takes 3 energy slots, right? So this is an issue, right? 3 energy slots will do 2 damage to the ogre, or reduce my kill ogre ability down from 3 to 1. So the ogre will be hurt, as an example. Maybe it's even going to be hurt enough where they're going to run away. So that's something that I might choose, fireball. But if I use 3 slots, that means the only thing that I can do is heal at 2. And if I choose the discontentment, right? If I try and figure out to reduce my discontentment, and if we think about this, the best combination might be something like a lesser healing spell followed by a fireball. Lesser healing, right? What it's going to do is going to change my discontentment down from, again, we're talking about a couple of actions here that are happening at the same time, right? So we're going from 16 plus 9 to 4 plus 9, right? 4 plus 9 would be a 13, from 25 to 13. And we're doing that just because we are doing a lesser healing. So that makes sense, right? But the ogre gets closer, right? The ogre is getting closer to you. And now we blast the ogre again. So we blast the ogre, and the ogre takes 3 energy slots. So the ogre goes down to 1, right, as an example. And it seems to be the best algorithm, because if we did this, then it would go from a 3 down to a 1. And then if 3 went down to a 1, then your discontentment would be the lowest when we did that. So again, we're going to choose the best result. So lesser healing leaves her in a worse health position than greater healing. So, so we choose the latter. So greater healing would actually be, think about it this way. The best combination would be this one. So you could actually survive the ogre, right? But this part right here, I might choose this one. Think about this, right? Because if I chose this one, heal 4, what's the discontentment? If I go from 4 down to 0, right, then I have a 0 and plus 3 times 3 is 9. So I would go from 25 to 9, whereas healing would only take me down to 13, which means greater healing might be something I want to do first, which takes 3 energy slots. And because it takes 3 energy slots to do greater healing, I can only do lesser healing next, which means I would die because of the ogre, because the ogre would continue to come at me, and it wouldn't be a pretty picture, right? Does that make sense? So, again, I think something like this, and again, it's flawed. It's not exactly perfect. We could certainly take into account, how many charges, what do charges mean for a particular wand. That can be very complex. But we can say that, for example, if I only have a combination of 3 and 2, then I want to be able to, have charges left, and evaluate more than one set of actions, more than one set of things in the future. That's a very difficult evaluation scenario, right? Even people make mistakes like this, and they choose the greater healing as opposed to using a lesser healing in a fireball. Okay. Other things to note that we can possibly do here when it comes to for this kind of situation is we're rating the kill ogre scenario low, right? But one thing we haven't done here, and we're going to talk about this a little bit when it comes to utility theory in the future, is what is the weighting for these things, right? So sure, healing is 4 out of 5, okay, on a 5-point scale. But maybe the ogre is an imminent threat that's going to kill me, right? That's going to cause me to die, right? So, maybe the kill ogre thing has a higher weighting than what we're giving it, right? So it's not going to go up by 1 point at a time as the ogre gets closer. Maybe it's going to go to a 5, right? When the ogre is within the, within, just out of combat range, because it's coming for you, right? So maybe it's going to go to 5, which means we have to deal with the ogre, right, as much as possible. The other action that's not in here at all is flee, which might be the other really good action. Sure, your healing might not go up, and you might have other criteria, like things like your food might go up or whatever, but you're not going to die, right? That doesn't make any sense. So again, this is a bit of a flawed scenario that is presented to us here. But I think the good thing about it is it gets you to think about how making a set of criteria isn't enough. You have to do a little bit of planning and kind of do some debugging when it comes to, hey, this could happen. What is this? Is this acceptable for me? Do I want to choose something like this that allows me to get killed because I've chosen the one that has the greatest, that reduces the discontentment of the entire character the most? Okay. Nicholas says there's a Minecraft mod that works like this. Okay, interesting. Nice. Let's talk about something else. Another scenario, another possibility, right? So again, we've talked so much about goal-oriented behavior, and we've done goal-oriented behavior in that discontentment changes over time. We've talked about timing. We've talked about how we want to affect discontentment by this idea of, how one action can have an effect on multiple goals. But there's another approach. So we can make something like more of a sensory perception simulation. So in this model, each motive that a character can have, such as eat or find information or whatever, is represented as a kind of smell, actually, and it gradually diffuses through the game level. So objects that have actions associated with them give out a cocktail of these smells, right? One for each of the motives that the action affects. And an example is an oven might give out the I can provide food smell, while a bed might give out the I can give you rest smell. Okay, so that's kind of smelly goal-oriented behavior. And so the way you can implement this is that you have the autonomous character follow the smell by using something like Pathfinder, right? So a character that is extremely hungry, as an example, would follow the I can provide food smell to find its way to the cooker, right? Whatever that is, right? So again, it's going to do something that is going to achieve its goal, because I might have a eat goal, and I'm going to go to that goal based on the desire that I have, to using the smelly gob approach. So this approach reduces the need for complex pathfinding in the game, because you're going to basically just go to the thing that's going to satisfy your goal. If the character has 3 possible sources of food, then the conventional goal-oriented behavior would use some kind of pathfinding algorithm to see how difficult each source of food is to get. So I have like 3 different sources of food. That one's farther away, or maybe it's more complex. We can actually put it inside, the time it takes, the discontentment that's going to go up, and all that kind of stuff. We can create an algorithm where we use the difficulty. We kind of create a difficulty rating for us to, satisfy that goal based on the smell that's coming from a certain, kind of location, a source of the resource, if you will, compared to another one. Okay, so that kind of thing. And then the character would then select the source that was the most convenient, which would be like the easiest to get to and the quickest for it to satisfy its goals. So that's smelly goal-oriented behavior, a different approach. Okay, interesting. And any questions around that before we get into rule-based systems, which is another way of doing dealing with goal-oriented behavior in some ways. Different decision-making algorithm. So again, I think really great stuff here is that the stuff that we're talking about here with goals can incorporate nicely, into your campaign, into your game. As an example, if you have non-player characters, especially if the non-player characters have goals, and your character has to satisfy their goals in order for them to do things like trade with non-player characters, maybe become friends with non-player characters, or maybe they want NPCs to come along with them and fight next to them, right? As an example, as like allies, if you will. How can that happen? Well, you need to satisfy their goals. What if you, the idea of alignment, here's another one, the alignment idea in D&D, Dungeons and Dragons, moral codes, that kind of stuff. That could be another set of goals or beliefs that the character might have, your non-player character. So let's suppose you do something that really makes them mad. And we've seen games like that, for example, in Fallout 4, right? And other games that Bethesda has made. If you have a companion character and you do something that's against their beliefs, their goals, if you will, right? They'll actually say that, this person didn't like that, or this character loved that, that kind of stuff. Because what they're saying to you is keep doing that because it's satisfying their goals. Because let's say, for example, you're attacking a super mutant. Well, you know what? The Brotherhood is probably going to be happy that you're attacking a super mutant, right? So, and the reason for that's happening is because you're satisfying them. They might have a goal like kill all super mutants and all other kinds of things in the game world scenario, and you doing that is satisfying their goal, and that's why they're sticking around and fighting with you. So again, really interesting ways of combining or thinking about AI, not just as adversaries, but as non-player characters, as strategically adding them as allies, or working with them in the game world and creating a scenario where it's much more interesting, a game world that's much more interesting than just enemies to fight. Okay. All right. So let's talk about something else now. So we talked about goal-oriented behavior, and now we're going to be talking about very, very briefly about something called rule-based systems. So what were they? Again, kind of used nowadays, but it's something out there, largely used, kind of through AI research back in the 70s and 80s, huge. They were also called expert systems at the time. Nowadays, they've kind of been, we don't talk about them as much because of deep learning and machine learning and a bunch of other stuff that's out there these days. But they've been used kind of off and on for the last 20 to 25 years, I would say, despite having this reputation for being inefficient and difficult to implement. Okay, let's talk about why and how they can actually help. And I still think, when the things that I've read and stuff that the book also supports, that they're not a real common approach because a lot of the behaviors that they have can be done a lot easier now and quicker with decision trees and state machines. Okay, so we'll talk about this anyway because they're out there, and it might give you another idea as a potential AI designer in the future about how to do things in a slightly different way. So, okay, again, so they do have their strengths, and especially when characters need to reason about the world. So let's say you're non-player characters out there or your autonomous agents, and it's something that you can't anticipate by building it in, by hard coding it into your decision tree. It's just like we're asking you to do last week in Lab 7. Lab 7's idea was, hey, let's try and build in a set of decisions and actions, based on our fixed set of scenario in your decision tree. What if there's something you can't anticipate? So this is where a rule-based system comes into play a little bit better. So again, is its it justifies its reasoning. That's the idea, that this is the reason why you want to use a rule-based system. And what it also does is it aids in something called content creation, okay, which we talked about many times before as well. Okay, so they have a common structure, rule-based systems. It doesn't matter which one we're talking about, or one that you might create homegrown, or you might use something that's out there already. They have two parts. One is a database containing knowledge available to the AI, some kind of database of knowledge. And the stuff that's kept in the database they're called datum. We'll come back to that in a second. And then a set of if-then rules. All right, if-then scenarios. Again, going back to what we're doing with state machines, we go back to thinking about if-then-else. We're like, wait, what? Why would I use if-then-else if I can use a fully fledged state machine? Rules can examine the database to determine if their if condition is met, and rules that have their conditions met are said to be triggered. Okay. A triggered rule may be selected to fire, right? So to act, if you will, whereupon its then component is executed. So we're checking to see if the if condition is satisfied, and then once the if condition is satisfied, that is, we can say the rule is triggered, and then the then component is actually going to be executed. And many rule-based systems also add a third component, which is an arbiter, that gets to decide which triggered rule gets to fire first. Okay, so that's something that is also there. And the scenario might look something like this, okay, where we have a set of rules. If my ammo is less than 10, then do something. If healthy, then do something else. And then we have a database, right, of information. Remember, the database of information is something that the enemy or the autonomous character knows about. For example, ammo is 4 and I'm healthy and the enemy has been sighted. All right, so those are the things that we would know. So the arbiter would say, okay, so which one of these rules makes sense to go with? Well, if my ammo is less than 10, then maybe I need to, and since ammo is 4, then this rule is triggered, whatever this rule is going to make me do. Maybe I need to reload, right? Or go get ammo, from the armory or something like that, right? I'm healthy. So if I'm healthy, maybe that means that I'm also going to be able to, attack if I need to. And there might be another rule that says if the enemy is sighted, then, attack the enemy. So which of these 3 rules am I going to go with? Which ones are the most important? Well, if I only have 4 ammo, I'm only able to take 4 shots at the enemy. Maybe there might be another rule that says if the enemy is big, right, then, if then. So these are all kinds of things that might be there. And again, when you think about the rule systems like this, you might be like, well, this is definitely inferior, to some kind of decision tree or a hierarchical state machine or something like that. But there's some stuff in here that's interesting because you can use rule systems to kind of react to a large number of scenarios that go outside of just a simple decision tree or state machine. So again, let's think about the action condition rule, what that is. So it causes a character to carry out an action based on finding a match in the database, right? And then actions could run outside the rule-based system. And though some can be written that directly modify the game state itself. So that's something that can also happen. Actions can still fail. That's one thing to also note. And they will only update the database if the action succeeds. So the database is interesting. The database of all knowledges. Let's take a look at an example. So the captain's health, this is the database. The captain's health is 51. Johnson's health is 38. Sally's health, that's right, Sally. Sally's health is 42. Whisker's health is 15. The radio is held by Whisker. So this is the known information in the database. Okay. Here's some rules, right? Whisker's health is less than 15 and the radio is held by Whisker, right? So that is maybe a condition, right? And we might have an action related to that condition, right? So is Whisker's health less than 15? No. And is the radio held by Whisker? It is, but it doesn't satisfy both conditions, so therefore that action doesn't trigger. How about the other one? If Whisker's health is 0 and the radio is held by Whisker, then Saleh pick up the radio, right? So it's interesting what it can do by looking at a bunch of conditions, a bunch of things in the knowledge database, if you will, to do something. And one thing that this can do is, again, it's nothing. There's nothing to say that you can't combine some of this idea with the things we've talked about already with goal-oriented behavior, right? So maybe this is the database of knowledge. The knowledge that your system has, not necessarily the specific AI agent. Okay, but it's going to direct the AI agent just like a game manager or some kind of game controller. The game controller object itself, if you think about it, this almost like a central command, if you will. And the central command is going to be, or HQ. Let's say you make an HQ system. The HQ system is going to basically control all of the autonomous agents, together, which is different. It creates almost like a strategy for how things are going to work, which is a lot different than just one individual agent, what they're going to do, right? So that's kind of a different approach, different thinking, as opposed to just individual agents. So again, we can say that the next example shows that the rules can be incorporated directly into the database itself. And then we add a rule shown at the bottom of the slide that governs what happens when a certain condition is met. So there's two functions. There's the remove function and an add function. The remove function will remove a portion of the data from the database, and the add function adds a new item, which could be an action to take. So this is interesting where the database can change based on what happens with your conditions. So here's the database. The database is 1,500 kilograms of fuel remaining. We're 100 kilometers from the base, and enemies are sighted. There's an enemy that's 42 and an enemy that's 21. Okay. Currently patrolling. That's the state that we're in right now. Okay, so a bunch of different conditions. If the number of sighted enemies is greater than 0, true, right now, and we're currently patrolling, true, then what we want to do is remove currently patrolling from the database. Think about this almost like a stack of information that we might have, right? And add attack first sighted enemy. So attack first sighted enemy is part of the database as an action, right? So that's something that is the new state that we're going to take, right? First sighted enemy might be enemy 21 or enemy 42. Don't know. Okay, so that is kind of interesting, a way of doing things. And using this idea of having a database of knowledge and potentially action states, the database is going to take care of states, is interesting because what it can do for us is, again, is it can create a more complex scenario for enemies or for autonomous agents, let's say. Okay. So this, again, think about this. This is not just for potentially one enemy, but a number of different ones altogether. A governor, if you will, or a game state manager for the entire, a bunch of enemies, or a bunch of agents, not just one. So there's a couple of ways we can do things. There's some things we can think about when it comes to rule-based systems. One of them is called forward chaining, and another one is called backwards chaining. So what is forward chaining? It starts with the database of information and repeatedly applies rules that change the database. And this is frequently used, okay, something that happens. So some kind of database, the database is going to continue to change, and the rules system, the rule itself, is going to update by adding and removing elements from the database. And when we add, remove elements from the database, what it does is it adds and removes possible actions. Again, really great idea. If you think about it, it creates this idea of an expert system because you're going to have a different set of actions. Think about if I go back to the scenario with this database and instead of currently patrolling, that is the state. That's the action that I'm taking right now. Maybe you can actually incorporate this with a decision tree or a behavior matrix of some kind, right? And if you think about this, you can remove, states and add new states. Incorporate this with a state machine as an example as well. And it can be done on the fly. And so you can have different kinds of action sequences or action trees that you might take depending on the situation, the rules. Okay, so you're a friendly NPC as an example, but if the character attacks one of your team members, then remove trading trading's not on the table anymore. Add attacking, right? Attack the player, because trading is not on the table anymore. It wouldn't even be in that database anymore. When you go back to that person the next time, trading is not even going to be an action that's possible. Okay, maybe if you do something to apologize, you give them money, you have another option to get attacking out of there and put trading back into the database. Okay, that's something that maybe you want to think about. But neat idea, where you kind of have a database of knowledge, that's held by either the enemy or some kind of game manager. All right, backwards chaining, it starts with a piece of data that could be considered a goal, and then the system works out a series of rule firings that would lead to the current database contents to the goal, and looks at the then contents to see if it could generate the goal. So again, not as common as something like this. Let's talk about the database a little bit. So each piece of data in the database should have an identifier and a value. And a Boolean could be the identifier, right? Some kind of Boolean, true, false. And here is an example. My fuel is equal to 1,500 kilograms, and my patrol zone, that's the Boolean. I'm in the patrol zone, true or not. I'm in the patrol zone, right? And we're going to use the word datum to represent one item in the database. So every piece of item in the database, for example, here I have 4 datum, right? So that's how it works. So 4 pieces of data, if you will, right? Symbolically, datum will be presented as some kind of identifier and content, okay? And then where the content is either a value or a list of datum objects. So it could be another list, all right? And the database, from the second example, can look like, let's say, the captain's weapon, maybe the rifle, right? And the rifle has a content, which is ammo. But ammo itself is a piece of datum that also has a value, which is 36. So the rifle has ammo, but ammo has a value, right? And same thing with Johnson's weapon. Johnson's weapon might be a machine gun, right? That's in the database, and it has an ammo value of 229, right? So ammo is the datum that's inside of the machine gun. So you can almost have like nested pieces of data, if you will, okay? So kind of neat. Each datum object could consist of other datum, which of course is composition. And we can illustrate this hierarchy of datum like this. Captain, as an example, contains a weapon, and the weapon is a rifle, and the rifle has ammo, right? And the rifle also has clips. So the rifle contains both ammo and clips, and each clip might have, as an example, its own amount of ammunition, okay? Health is also something that is a property of the captain, right? It's another datum that the captain contains, as an example, because this is inside of the brackets, right? And position in X, Y, and Z, might be also something that is contained for the captain. Again, typically I wouldn't do this. I probably would put the position, hold the position information inside of a transform that we've seen, in most modern games. But you could do something like this. Health is neat, and you can do other things, not just health, but also goals, a bunch of other stuff that makes sense to put in the database for the captain. So this information, the way it's encoded, is something that we want to be able to, to capture. Make sense? And I think I lost the other example. I had it down here, but it's gone. So, so this is interesting. So some of the ways one rule might be chosen to fire over another rule, let's go back to rule arbitration for a second, is we could look at the first applicable rule. Okay, so whatever the first applicable rule is, that is definitely a way of doing it. The other one is the least recently used rule, right? So again, why is this happening? Because if you're using the same rule over and over again, remember we talked about determinism, it becomes something that if your AI is deterministic, then you can predict it. We don't want that to happen. We can even go with something like a random rule. Choose a random rule that applies, right? One of the random rules that meets the criteria, because there could be multiple rules to meet the same criteria, okay? And you could have the most specific conditions. So We can look at specificity. So, for example, if there's one of the conditions that's more specific than the other, almost like a condition chain. Okay, and the last one is almost like a dynamic priority arbitration, where we have a set of priorities for the rules, and we could change the priority of a particular rule based on its goals. So, really neat way of capturing, kind of making decisions. And again, as a summary, we've covered really two different scenarios, and both of those scenarios they're not mutually exclusive. It's not like I only have to use rule-based systems, but I'm not going to use something like goal-oriented behavior. It's not like that. And it's not like in goal-oriented behavior I can't use a decision tree or or some kind of behavior tree. It's not like that, right? You can combine all the things that we've talked about so far to make a much more complex scenario for an AI agent. Okay, so questions around the stuff we've talked about today, because that's really the content that I wanted to cover. I know this is kind of a high-level theoretical thing that you're looking at, but again, we have to consider a couple things, right? That your job as an AI designer, if that's where you're going to go in the future, because game development is huge, right? And you're going to choose some kind of specialization, guys, all of you, at some point or another. Maybe there's not going to be a specialization. You're going to start off as a generalist or a tester or something, but eventually you're going to, I don't know, kind of land in a position that's the most comfortable for you, the most interesting that you want to always try and be in. Maybe AI is for you, and you want to think about being an AI designer. AI itself has several subfields, like, for example, like, I don't know, some kind of gameplay AI, or maybe you're doing things like when you're not in combat, you're doing some kind of non-player character AI, or some kind of strategic AI, or something else, right? So the things that we're talking about could be used to, and kind of inspire you to think about, well, what kind of AI would I like to create? If I was going to make a role-playing game, do I want to include something like a rule-based system, or do I want to include something like goal-oriented behavior for some of my non-player characters? What do I want to do? And I think the answer should be probably yes, right? You probably want to include something like that, other than just a decision tree, state machine, or a behavior tree. Those are very lower level kind of actions and reactions. Okay. All right, so let's talk about Lab 7 briefly. And again, Alex is going to give you more details about this as we get closer. So we created a path node class already. That's something that we did. We're going to build move to player action or something like this. There's a few actions that we talked about, right? So move to player action, move to line of sight action, move to range action. We haven't really done those yet. And those actions, remember, we have a series of conditions, and those actions are going to be something that we've asked you to do for your assignment 4, right? So we're going to build some of these and to help you with how assignment 4 can be done. And the only way these actions can take effect is if we're able to detect line of sight. So I have already a line of sight mechanism that we've talked about in Lab 7, Part 1. We said, okay, we have line of sight. Cool. But we haven't done anything with that. We haven't kicked you out of patrol mode into attack mode or something like that. That's not the case. And in fact, Lab 7 Part 1 should be enough to get you basically finished your assignment 3. Okay, that's what it should be enough. Now, there's a lot of elements that are missing from assignment 3, and I wanted to talk about that really briefly one more time before we get into that, because I know I keep talking about it, but now that assignment 3 has been extended, we have a chance to just quickly talk about these things again, just to further clarify, the things that we're asking you to do, right? So we don't want you to be freaked out, or, we don't want you to say something like, well, it's undoable, I don't know where to start, or those kind of things, right? So again, let's go back to assignment 3 really briefly. So again, assignment 3 due this Sunday. It's been moved. Okay, just to reiterate. So one thing we've said is mandatory criteria have to be completed in order for you to pass this assignment. Okay, so not filling in the 18 points in your place scene, not doing this kind of stuff, or not working on your play scene doesn't make any sense, right? Because your play scene is going to be where all the action happens, right? That's why it says play scene mandatory, including a node class. you must create a collection of node pointers, right, to enable iteration across all nodes. Okay, we kind of did that for you, right? Ensure you select an appropriate actor sprite. Now, this is on you, like we talked about. That you're going to be able to move around, right? Create an interesting map that is overlaid on top of the nodes. This can be a Brick Creative map. You should have that already in place, or thinking about your stuff, some kind of image set, if you will, right? And your play scene must include appropriate background music and sound effects. Again, all of this is mandatory, and you could have been working on it this entire time. You didn't have to wait for us. All right, other requirements. A debug view we've talked about. We've been working with you on it. Debug keys you can add as basically inputs. Player animations and sound effects. Again, nothing to do with us. This is something that you can incorporate on your own. Player combat capabilities. Again, one thing that you want to think about is what is close combat distance and what is range combat distance. How do you figure this out for your player? Okay, because you're going to have a player in the game. This is something we haven't covered in the lab. We're not giving you information about how to make a player. That's something that's coming from your fundamentals class, right? Player health bars and game status. That's all stuff, again, that we've covered in, you were shown, or we discussed it in your fundamentals classes. And if not, how do you do this? How do you do a health bar, right? I mean, really, it's a rectangle, a couple of rectangles. One of them that has a background that's black or red, and another one that has a background that is green, and you layer them on top of each other. So a couple of different of objects, one on top of the other one. And what you're doing is you're changing the scale of one object, as an example, while the other one stays the same. Okay, so the kind of like the scale isn't changing. So a very simple way of doing this with from a health bar perspective. Some people can take it further and make a whole health system. And the health system might be something that is part of a class. Game status is like another bar, but it's a progress bar that kind of shrinks or grows. It really depends on how you do it. If you're making a game that you have to complete in a certain time, then the progress bar continues to go away until your player hasn't satisfied the requirements. Then you lose the game. Or maybe what happens is you need to set a bunch of different checkpoints. Hit a bunch of different checkpoints, and your progress bar can get bigger and bigger. So this is something that you need to do. The checkpoints for your assignment 4 are going to be how many enemies you kill, right? Maybe you have a bunch of enemies that you want to kill. The default is 2, right? Obstacles, we've given you examples of how to do obstacles. You can use bricks. We used clouds in the last lab. Lots of opportunities to make it your own. Base enemy class, where the base enemy is going to do what they're doing right now, where they're kind of kind of moving around the screen. Our base enemy in Lab 7 is the spaceship. No, only one. We're talking about assignment 4, Jack. So the base enemy only needs one. There's only needs to be one enemy. I mean, you could include both, like 2 of them to attack if you really want to. It's really for you. We're giving you the minimum requirements to make this work. Okay. So you can have 2 enemies that are patrolling if you really want to, but the minimum is 1. Okay. Obstacles, at least 4 obstacles. Okay, that block line of sight, but don't block detection radius. Those things you need to put in place, right? Animations and sound effects for your enemy. Now, our lab does not satisfy this requirement because our lab does not have animations for the enemy, right? Our enemy is just a spaceship. A spaceship without animations does not satisfy this requirement. So please pick an object that meets this requirement. That's a 5-mark loss if you don't do that, right? Base enemy line of sight. Well, we have our spaceship. It has line of sight. That's kind of like the base enemy, right? And the line of sight does work, but it says each base enemy will need to calculate and keep track of whether or not they have line of sight with the player, okay? Well, right now it keeps line of sight with the target. Well, if you think about it and if you work it out, if you can move the target around with WASD keys, right, if you think about that, then in essence, that is the player character. It's like you're taking the target, you're taking control of the target in the Lab 7. That's what you're doing. Not with, as an example, the I am GUI keys, but actually giving yourself WASD and animations and a bunch of other stuff that you can do, right? Base enemy detection radius. We didn't do detection radius in class. We didn't do this part, right? This is not that difficult to do. Detection radius is an overlap circle. That's what you're doing there. Circle versus the players. You're doing a collision manager check, circle and AABB, let's say potentially, or circle, circle. We've talked about these kind of things with you before, right? So really, there's not a lot that we haven't covered right now when it comes to the AI portion. The stuff that you need to cover are, the mandatory components that we haven't covered, the animation, the movement, the damage, the death, all these different kinds of animations for the enemy base class that we do not cover and are not applicable to our little spaceship combat that we've made. We're not covering that for you. You need to do it yourself. So clearly, if you're going to make it a spaceship, then maybe if you're going to do an idle animation, maybe the spaceship has some kind of idle animation, like a force field or something like that. Maybe your movement animation, and other related sound effects, maybe it kind of stretches when it moves. That's a kind of a different kind of animation, right? Maybe the damage animation, there's fire particles that come out of the spaceship. I'm just making this up here, right? Or maybe the spaceship seems to, be venting plasma or something like that. Okay, and the death animation, maybe the death animation is an explosion. These are all possibilities when it comes to making a spaceship, if you wanted to use this scenario that we're talking about here. Where I'm challenged, if I was going to be challenged to do what we've asked you to do, as we said, select appropriate actor sprite, and it could be a spaceship or something else, but then we ask you to do something like, well, the actor requires some kind of player animations, some kind of idle animation with no input triggered, a movement animation, and a close combat animation. Well, I don't know about you, but no spaceship I know can close combat, right? It doesn't work like that. Unless the spaceship has an arm, some kind of weird arm, or I don't know, a claw or something like that it can attack. So could it happen? Yes. Is it probably likely you're going to use a spaceship in this scenario and for A3? Probably no, but something like maybe a dreadnought or I don't know, some kind of I'm thinking of a robot might be better, right? Because a robot would have, Gundam, that might be okay as well. But anything like an actual spaceship, like Star Trek spaceship, there's no close combat for that, right? So that's something that you have to think about how to have it, because these are requirements for your for your game that you're making. And really what you're asking you to do for A3 and A4 is kind of two parts of the game. Kind of the first part, which is your base class and movement and your scenario, your background, things we've helped you build in lab 7. And the second part is all of the behavior for your AI, right? So that's what we're asking you to do. Okay. Questions around A3. Around the corner, if you don't have any questions, around the corner is A4. Remember that A4 depends on A3. I'm covering this again for you guys. Again, I've had several interesting emails come at me saying things like, so for A4, do we have to use A3? Can I make something new? No, you cannot. You have to use A3. You have to use A3 as a base. It tells you that right away. It says must use A3 as a base right here. It's mandatory, right? So don't start off with something completely different for A4, right? So it has the patrol action. We just kind of talked about that, and there's going to be several actions that we haven't covered, but all of these actions are things that we may cover another one with you this week as an example when we modify our scenario. But really you're making two different loadouts, right? Here's loadout A, which is your close combat enemy, and there's a whole other loadout we're making, which is loadout B. Well, this is where, Alex was talking about it and saying maybe what we do with you guys is we incorporate the decision tree inside of your close combat enemy or your ranged enemy, and so that there's two different kinds of trees, and there would be, right? Because this tree for the close combat enemy is going to be different than the ranged combat enemy. They're going to do different actions. The two trees don't make sense. It's not one tree that's enough to cover this scenario, both scenarios, right? Because one decision tree is going to do the patrol action, and then it has move to line of sight, move to player, and close combat. Okay, well, no, but not this one. This one doesn't include close combat. So you have to use a different decision tree for ranged combat if you're going to go that way. compared to close combat. So please keep that in mind, that there's two different scenarios here. Two different loadouts mean two different decision trees or two different decision-making algorithms. Okay, it's up to you. Do you have to use decision trees? Could you use something like, state machine? Yes, you could use state machine. You can use the decision tree. You can use a behavior tree if you really want to. Could you use goal-oriented behavior? Yes, I guess, but it probably is kind of a overkill when it comes to what we've asked you to do, because there's not really any goals that these things have other than kill the player, right? So, and keep healthy. Those are the two goals, right, that we have. So, destructible environment, keep that in mind. So when you're making assignment 3, build in the health bars early to your objects. Don't wait for assignment 4. If you already have a health bar, adding it to an object should be something that you can do even in assignment 3, right? And enemy spawning and the win condition are things that you can think about how you're going to plan these things when you're working with assignment 3 already. So stuff that you can already start doing for the assignment 4 before you even start it, and you can incorporate it into assignment 3 so it meets the requirements early. Okay, so that's assignment 3 and assignment 4. Questions about any one of these two before we go for the day? Because I know I've kind of talked about them before, but the challenge with us is I talk about them and then I get a slew of emails that say, so do I need to use assignment 3 for a basis of assignment 4? And the answer is yes, you do, right? So does that make sense? And you're making a little game. It's not just, using our assignment framework and following the labs like one-to-one, and then just basically handing us back a lab for an assignment. The lab will not be sufficient. It will not meet criteria for the assignment. It won't. You won't pass with the lab. Okay? You have to add more to it. That's part of the assignment part, right? I'm hoping that helps your understanding of what we've asked you and the criteria. Any questions at all before we go for the day? Okay, here's one. Jack's asking, how big should we make the line of sight radius? You're talking about the detection radius. Line of sight and radius are two different things, right? So, yeah, so the detection radius is really up to you. I wouldn't make it so it's the whole screen, that's for sure. You might want to think about making it so that it's probably, a good quarter of the screen. Might make sense, right? And the other thing to think about is, the idea that the player has been detected, almost like a state or something that the autonomous character, your close combat enemy or your ranged enemy eventually will know. Has the player been detected? Yes or no? That is a state, right? That's going to almost like a Boolean flag that you're going to trip, if you will, right? So that's something that you need, because once the close combat enemy once the player has been detected, then you can no longer go and do patrol anymore. Patrol is not even an option, right? Going back to that rule-based system idea, if I've already detected the player, take patrol out of there. It's not even an option. Can't even do patrolling anymore, right? If that makes sense. So again, really neat way of kind of putting together. You can also make your almost like a little database or a list. We can call it, instead of a database, let's call it a list of possible actions you can take and or states. You can make a list of states, and then the action that you're taking. Maybe something that is the available action list that you can take is something that you remove if things change. I'm talking about strictly with assignment 4 as well. So example would be something like, okay, you're a close combat enemy, but you've taken damage. Well, guess what? You patrolling is out of the question, and you doing something like attacking is out of the question. If you're below 25%, your actions only flee, right? So you can do that differently than incorporating that into your decision tree. It's truly up to you. But again, it's got to work, and we're going to test it. You should be trying to stress test it. You should try. One thing that I've had students do in the past is create a close combat enemy and create a ranged enemy and have them fight each other, right? See what happens. Because basically what you're doing is you're just pointing to the other one as a target. What's my target? My target is the player, or my target is the other enemy. Try that, right? It's very interesting what happens. And you can see that's a real great way of stress testing your environment, because if one enemy fights the other one, if that's what can happen, then it's interesting how, how the game can work. One of them will try and keep its distance, the range one, and go behind cover, while the other one's trying to chase them, right? So that kind of scenario can really build a really great, you can find a lot of the issues that come out before you have the player in there as well. Everything is automated, which is kind of neat. All right, so that's A3 and A4. Any other questions? Jack's the only one that had a question about radius. Again, Jack, the answer is about a quarter of the screen max, is what I would say. All right, guys, if there's no other questions, I'll stop recording on YouTube. Um, and we'll go from there. All right. Yes, I saw your email. Thank you very much. And I'm talking about the people online. All right. That's it. Thank you so much, guys. I'll stop recording on YouTube and we'll go from here. Thank you.